Hi there, welcome to DesignSpark, where today we're going to be joined by Laurent from Wurth Elektronik, and we're going to be talking about capacitors. Hi Laurent, do you want to say hello to DesignSpark?
Hi, Greg. Thank you for this interview. My name is Laurent Völkel. I'm from Wurth Elektronik, field application engineer. I worked more like 25 years already in the company, was design engineer for explosions safety remote control. And before that, I was doing something for, today it will call multimedia. That time was just radio and television.
Well, yeah, I remember those days, absolutely. Um, Laurent, we obviously capacitors, passive component, but when you think about what they're involved in, they are a fundamental component of electronics design. So things like energy storage, power supplies, signal coupling, timing, frequency selection, voltage regulation, and even things like protection. So I just want to understand a little bit more about capacitors as we go through this conversation. If we look at energy storage, which for me is a really interesting kind of area to start with, what is it that is the capacitor's role within energy storage?
Well, after the resistor, I think the most used component in every electronic design is a capacitor. And then comes the inductor and the rest of the components. A capacitor has also a very simple role to store some energy for a very short time. It can charge fast, it can discharge fast. It can be used also like a instead of transformer, a small galvanic decoupling in a signal line or something like that. But actually, this is a simple passive component which has also some hidden tricks. Depends what kind of dielectricum they use, what kind of size they have. They could make a lot of trouble for the design engineer. And believe me, I did face such kind of things as well when I was design engineering, and I did not understand why this capacitor not working like it should, because I choose in the right way. I take the data sheet, I check the voltage, I check the capacitor, and still doesn't give me the response that I need. So there are some little tricks. Maybe I should share with you some information. When you talk about multi-layer ceramic inductor, ceramic capacitor, sorry, um, you can have something like a nomination like X7R. What means X7R? Nothing else, just the lower temperature, the upper temperature, and then the tolerances. So this is the third character. The thing is that all these different X7R, X5R, NP0, they have some different behavior, especially when you look now to this DC voltage dependency. So this DC voltage dependency is some of the point where many design engineer fell into this trap that they choose a 100 nanofarad capacitor for, I don't know, 25 volt or 50 volt, and they use it just by 12 volt. And they realize that, okay, I put this capacitor, but I don't see the influence of this capacitor, and they're wondering why. The thing is that they are voltage dependent.
Mhm.
Depends on the dielectricum. You can have a different voltage capacity drop. So I compare here different dielectricum like NP0, X7R, X5R, and look, if you apply to the 50 volt capacitor or NP0, which is not the first choice because it's too expensive. If you take now the X7R by using only 20 volt of this 50 volt or only 25 volt, if you go to 25 volt, you see that you will have a drop already almost 30%. If you choose the X5R, you will have a drop of 70% of his nominal value. And I will never choose a Wi-Fi-V capacitor because the Wi-Fi-V, it's actually, I think this is a capacitor which is a virtual capacitor. You can see it, you can pay it, but you will not have the capacitor any in your circuit. It's just something good to make it more heavier, the PCB, but nothing else. So this is my opinion about this capacitor. I'm so happy that we don't produce such kind of capacitor. But you can see what is the big influence of this different dielectricum, only just by the voltage. And all this information, you can get that very fast. Again, if you choose website where you can find v-online.de or .com/redexpert. And when you start this online tool, you can choose something like capacitors. I will go to the multi-layer ceramic capacitors, and I will choose a capacitor in 1 dielectricum X7R. I will choose the 50-volt capacitor. I will choose a value which is exactly, what is my value here? 1 microfarad, only the 1 microfarad. And I will compare a X7R 50-volt capacitor 1210, and I will look at 1210 size. What is the behavior DC biasing? So I have a 50-volt one, but that 50-volt will have less than 50% of his nominal capacity. I will use that only at 24 volt. At 24 volts, I will have something like 12% drop. And then some sales guys come to you and say, oh, why you use a 1210 size? You can choose a smaller one. And look on the data sheet. We have the same characteristics, same voltage, same dielectricum. We have the same capacity value. It just you save space and so on. And then you choose instead of 1210 or 0805 size. And look what happened to the 0805. Same dielectricum, same voltage. At same voltage, you will drop now at 24 volt. I try to put the 24 volt exactly here. Oops, my cursor not working. I will try with this one. It will drop in the same value already 42%. Now, what is your expectation if the sales guy tells you use 0603? It's still perfect.
Mm-hmm.
I will choose now 0603. Already at 20 volt is dropped 20, more like 80%. So from your 1 microhenry, you have only left 20%. And then you're wondering why your DC-DC converter, the ripple, it's not dropping, or why you have EMC noise, because it's still the capacitor you put there. And then you think, oh, I have to put more of them. So instead of put 10 pieces in the row, choose one, the right size, because it's not only data sheet, it's physics, it's behavior of this dielectricum. And I will not compare to 0201 or 01 or 01 or 05, because it will be ridiculous. So I would say 0603 if you have really something extremely small, like a Bluetooth dongle, or maybe okay, when you design a hearing aid, you will not have 24 volts there. Then you can use the 0201 or even smaller size. But anything else, if you have space, please use the size which is fit to your design, because you will not face this behavior of DC biasing. Especially MLCCs, they are very extremely DC biasing.
Yeah, that's a really important point to consider. You know, again, we're seeing the specification on the data sheet versus real world application. The data sheet obviously is a guide, but the real world application, knowing a little bit more about where and how the product's going to be used, that takes the design consideration predominantly maybe more meaningful than just what is currently on the data sheet. Would you agree with that?
Yeah, absolutely.
Yeah.
I can share another nice picture. Okay, this is a power supply using a analog device LT8610 chip input 12 volt 5 volt output 1 amp output and switching frequency 1 megahertz. First, we did use an aluminum electrolytic capacitor of 47 microfarad, 16 volt. Output voltage is just 5 volts, so 16 volt is quite a big distance to have not this big biasing. But if you look on the aluminum electrolytic, the electricum, it has a high ESR and ESR value. So the delta voltage ripple, it's 400 millivolt, peak to peak. Now, in the same design, just desolder this capacitor from here, just desolder it, and change the output capacity from aluminum electrolytic also 16 volt, also 47 microfarad, and will happen following. Because of the ASL and ASR, it's much, much smaller. It's a polymer. The peak to peak, including the high frequency spikes from 400 millivolt, is dropped to 50 millivolt.
Mm.
Only just changing this small, because it fits the same pad, we change from aluminum dielectricum to polymer. Now, if you want to improve even this one and change from polymer to MLCC, also 16 volt, also 47, but quite a big size, 1206, not 0201. Now we have only just 4 milliohm ASR and 1 nanohenry ASL. Of course, also the footprint and also the PCB layout is crucial in this case. You cannot make excellent capacitor and you have extremely long traces for the ground or to the capacitor connection, because every parasitic it will destroy the efficiency of this capacitor. But now from 400 millivolt you go down to 40 millivolt only by one single component, which is just nothing else, just a simple capacitor.
Yeah, absolutely. Again, you're highlighting design considerations there. You know, parasitic capacitance. All of this needs to be taken into consideration in the actual design itself. I'm really finding this conversation fascinating. Like we said at the beginning, the capacitor is used for so many things within electronics design. So if we think of, you know, one of the main things that we're always every piece of equipment needs is the power supply.
Yes.
Why is it in power supply filtering that the capacitor is really important?
First of all, because I have a lot of friends which they know me that I'm electronic engineer. They bring me sometime devices to fix it because they tell me, Laurent, you're an electronic engineer, fix it. The first thing what I'm looking to them is to change the capacitor. First of all, the capacitor is something which is damaging the first time. They have a lifetime, especially when you apply to the electrolytic capacitor too high ripple current, they get hot, and sometimes they are broken before 2 years. When you have the warranty of 2 years, you're happy that they will fix it or they will change your device. But sometimes after 5 years, you still have the device which is running quite good, and one day it doesn't operate, and the reason is mostly the capacitor. Whatever is the electrolytic capacitor, but sometimes it could happen that even it's just a wrong ceramic capacitor that was chosen, and that's losing also his capacity in time. This is something which for me was also new, because I didn't never imagine that a ceramic capacitor after a while can also losing his value. So that was for me something which I was really wondering, and I had in fact exactly this issue from one of the, I will not say the brand, it's a nice amplifier, a very well-known company, a big brand and a high quality brand, and I was changing all the electrolytic capacitor and still the power supply was not working. And I measure all the diodes, I measure all the transistors, everything was good and still was not running. And I was really almost frustrated. What's wrong in this device? And finally, I start to change the ceramic capacitor, and voila, by the second capacitor, I was the lucky punch that I find the ceramic capacitor which was not running anymore, so was not anymore coupling the pulse from PWM to the MOSFET, and I was like, it's impossible. This is a ceramic one, and I took to the LCR meter and I measured it, and I was like, you cannot see it on the electrolytic. Sometimes you can see this bulb on the top that is already exploding. Okay, this is an easy repair. Friends are very happy that I'm fixing in a very short time, but this amplifier took me few weeks until I fix it, because sometimes I just give up. I will say, I cannot do it. I'm too nervous. I don't know what to change it anymore. And then I find out it was a ceramic MLCC which was making this problem. And then I talked to our guys, which is a product manager for MLCC. Say, hey, no, yeah, we know that. Just show you some picture. Just find this picture, and I can show you also this picture. What happened to MLCC in time? So this is again NP0. They are very stable. You get something for the money. So NP0 is not just expensive because it's nice to have expensive. It is because it has a very, very clean dielectrical and excellent behavior. But look what happened to the X7R, X5R, and Y5V, which I don't like it, after just 1,000 hour of operation. And imagine what is 1,000 hour if you have a amplifier which has a standby, which is always connected to the power, 365 days, 24 hours. What means 1,000 hour in the dropping of his value? After 1,000 hour, almost 20% drop.
Yeah.
The X7R, X5 are not that much, but they are dropping. And if you have an amplifier which is 5 years long, always plugged to the main voltage, and one day will not stop or not start, that's the issue. Maybe of the ceramic capacitor, which was used was chosen on the not in the right way. Maybe the size was too small. Maybe the price was too low. We don't know. I don't know the brand which was because it was not market whatever the capacity, but anyhow it was something for me. Also knew why MLCC can lose his capacity in time.
Yeah.
So it's crucial product. It's a simple passive component which almost we say is the salt in the soup in the electronics because without capacitor no operation. But it's very important to use the right capacitor, not override by the ripple, to take care about the voltage dependency and of course size. Don't believe the downsizing campaign for all these people who try to tell to you, take the small one. I tell you why, because we make capacitors well. When you produce capacitor, you have a plate like a little bit bigger, like a A4 size. And when you cut at these spaces, 1210, you can maybe 1,000 pieces in the same machinery. But when you cut this ceramic plate to 0201, you can have maybe 100,000 pieces from the same plate. This is the only reason why they want to sell to small pieces.
Well, that's really interesting to hear that because there is an association between downsizing and energy efficiency and sustainability, everything that we're hearing. But in actual fact, you're actually going to be using more over time, if you see what I mean. But the performance isn't going to be the same. Like we were talking about earlier in terms of the design, purely looking at the data sheet is not just sufficient in itself. You have to consider the overall design of the product, where it's going to be used, etc.
Absolutely.
Yeah.
Absolutely correct. You need way more information just like a data sheet. This is for starting point, it's okay, but then you have to take in contact with the field application engineer or for the company who supply you this component and ask them more about this component to be safe, that this component will work. Actually, every electronic engineer, when he designs something, it want that to run forever.
Yeah.
I think this is opinion, my personal opinion. We know that is not possible, but if it's running 10, 15 years, it's time to buy a new one because there are too many already improvement in the design efficiency and not only size. Today, downsizing happening quite very nice because if you compare the charger from your mobile phone, that's the old heavy one from a brand which is Finnish company. You remember it was heavy, and now if you take something new, doesn't matter, it's a US or Korean company, it's light and it's much more powerful. It is because this influence of this GaN and SiC capacity, SiC transistor, that's making the device it gets smaller.
Yeah.
But for the passive components, they are not a big improvement like in a semiconductor. Then we can say, okay, instead of 50-watt transformer, you can take a small one. You can take that, but then you have to take in consideration, you have to switch to very high frequency. Very high frequency means you need a much better filtering because EMI will be your problem.
Yeah. The other thing of which is, I mean, there's so much to talk about when it comes to capacitors, for example. We were talking about filtering. We were talking about very, very different types of applications earlier on. But also in terms of protection. against protecting sensitive components. The capacitors are used for coupling, decoupling. Could you just maybe explain a little bit about how that actually works? What is it that we're protecting in terms of blocking DC, for example?
Yeah, for the DC blocking, it's actually quite very simple. Normally, the typical application, like in the audio input, you have a capacitor which should deblock the AC from the DC for the AC. But normally, this kind of, I would say, for more safety, it is this typical 1 nanofarad capacity which you put to the every each pinning of your input IOs, where you try to face this ESD discharging.
Mm-hmm.
So normally you have this kind of ESD discharging from static charge when you're touching any metal body, and then you have some blank connectors, whatever, and then you put this 1 nano capacitor to the chassis or to the ground to discharge this high peak of ESD. But in the fact, capacitor mostly they are for a short time to store some energy, to have the ripple smoothing down after the DC-DC converter, to store this kind of energy for very short time if you have some load change or something like that. It's always nice to distribute this energy not in one capacitor, at least to put 2 or 3 in parallel. I like if I need a calculation like 100 microfarad capacitor for my output from the DC-DC converter. Very rare. I should have extremely low space that I can put only just one capacitor. Instead of using one, I prefer to use at least 2 of them, or maybe split to the 3 times 32 microfarad capacitor. It's much better behavior because each capacitor have his ASL, ASR, and resistors in parallel. It's getting smaller and smaller and smaller, and then automatically my ripple goes down, and I have less problem to have ripple current or have a damage on the capacitor because of the ASR issue. I like to do always some splitting of the value. Whatever is input capacitor, output capacitor, I try to do the same. And if I use the 100 nanofarad capacitor, which is, I would say, the universal filtering capacitor, I always first check what is the frequency which I filter, because a 100 nanofarad capacitor above 10, 12 megahertz is not more effective. So if I need to filter 50 megahertz or 100 megahertz, doesn't matter how many 100 nano I put there, it will be not effective. I take LT-Spice, I make a small simulation, and then I calculate what kind of capacity is better for me. And I never use in a simulation software ideal component. I choose always from the library. We have also a nice library for LT-Spice on our website, or over in the datasheet sometimes it's linked directly to PSpice, Altium, whatever simulator, your cadence. You can use the simulation software with the parasitics. This is very important when you simulate for a capacitor, that you not consider them ideal components. I'm very sorry to inform you, it's impossible to build ideal capacity, except if you make your own PCB layer and make a capacitor of that. That could be a most ideal, but not a simple component. So use in the simulation the parasitics and consider all the components are parasitic. Inductance, LCR in parallel, capacitor, LCR in serial. Then you're on the right way, and then you can calculate and estimate a good value of the capacitors.
You're absolutely right. Those simulation tools are invaluable. To begin with, you can play with them, you can reassess the values, but obviously getting the simulation out at the end to show you it working, that is really, it's worth its weight in gold, really, to some extent.
Yeah, that's true. That's true. The most thing what I always see in the simulation software, when engineers start to simulate, they simulate only ideal component. This is the biggest mistake, because in this way you cheat yourself actually, because nobody can build ideal inductance, ideal diodes, ideal capacitor, and so on. That's the reason when I start to do simulation, it is because I cannot explain myself what is happening, and then I use the parasitics as well, because anyhow I will have some different parasitic which I cannot see or cannot explain what is happening, but at least I know that the component parasitics already it's included in my simulation.
Mm-hmm.
That makes sometimes the nightmare smaller, or they give you a better response, and you realize, oh, maybe I should use not only 100 nano, maybe I should change to 10 nano, and then your smile gets bigger and you see that the designs work.
Absolutely. It's the capacitors are obviously a passive component, but in their application, they're anything but passive. They're either creating protection, they're helping circuits to work better, etc. There's a few things I just want to cover before we finish. One of the areas I want to talk about is filtering, for example. So frequency selection and filtering, high pass, low pass, that type of thing. Can you tell me just a little bit more about why is that essential, for like audio and RF communication circuits?
Well, filtering, it's very important to choose also the right topology of the filter, because it depends on the system impedance between source and load. You have to use different filter topology. Not only just a capacitor it's good. If you have extremely high system impedances, only with a capacitor could be more like enough. But if you have low with high system impedance, you will need a LC. That's a low pass filter actually. Sometimes if you're not 100% sure, instead of using LC, I put a second C, so I have my P filter because it's CLC, and then I say, okay, with the LC, I have some result, but the P filter is much more effective. If I see that with the P filter, I still not improve my LC, it means maybe my system impedance is more lower impedance, so I go back to the LC and I give another L, so I have my actually T filter, and the T filter is acting in a lower system impedance, much more effective like a P filter or LC filter. And this is how I play with the filter normally. And like I tell, LT Spice is the better and the cheapest way, because it doesn't have to pay any license. You can use for commercial, you can use it everywhere, and you can make a nice simulation and you see the behavior, how this filter affects. It is just changing some components, or instead of using just an inductor, you can use a chip bit ferrite, which is much more effective and have a low Q factor for not ringing and so on. And then I choose the LC or T filter or P filter using with the LT Spice, and I can say, okay, 99% I know in this frequency range, if is that a differential noise filter, I will fight with this filter against that and I will solve it. If it's a common mode, no LC filter, no P filter is enough, because common mode is coming not only on one line, and it's coming also on the ground, coming also on the plus, and come also the data line. So you need to filter all of this line. Then you have to change back to the common mode chokes or to common mode noise filtering, and then it's a different behavior. But that's a very, very long story, and we can talk about that many hours.
Yeah, there's so much we can talk about in terms of the product, the technology, the design. It really has been a really good conversation today, and yeah, so I just want to cover a couple of things before we finish. We've talked about things like protection, obviously the campaign for downsizing, but also just what I really want to understand from yourself is hints and tips for design. Any hidden issues that we need to be aware of. We've already, you've already covered a lot of the design aspect, but I think it'd just be a nice thing to finish on, sharing your years of experience.
Well, when I would do today a new design, I always think already on the schematic to the EMI issue. I will put on the beginning on a 0 ohm resistor and keep a pad free for a capacitor for at least a LC filtering for my power supply or for my data line. Then the ESD issue is also very important. I will put also a pad, as small as possible, which is just fit to the connector in case that I will fail the ESD test, the final test after the EMI test. So that's something which today any electronic device needs this ESD suppression, so you need to put some TVS or varistors. You need to put some LC filter at minimum, or even maybe sometimes P filter or T filter, because as soon you switch something, it will generate some harmonics.
Mm-hmm.
And if you want to pass the EMC test by first shot, I think this is a dream of every electronic design engineer, to pass the EMC test by first shot. It could happen, but you need some good experience, and you need also a lot of luck, because you can simulate, you can calculate a lot, and still it could happen a bad luck. So if you want to pass, I know many people I know which passing the EMC test by first step, but it costs something. It means it costs some components, and it costs some experience. And if you pre-think already in the design that I have to face something, and that you are prepared for that. Maybe in the EMC lab, you can disorder this value, and you can put the right value, because you was thinking that you will have a problem at 10 megahertz, but it is a 100 megahertz. And then you have the pad to solve. You don't need to redesign the PCB layout. As soon you redesign the PCB layout, the parasitic is changing as well.
Yeah.
So I like to have already prepared at least something on my prototype that I can do some improvement, and the rest is experience. It's like my children. If you tell for the children the candle is hot, don't touch it, they will touch it. Same is EMI. You can tell 1,000 times, they will still make the mistake until they will burn your finger, and then you will start to improve your design with putting some ferrite bits and some right capacitor for right value.
Yeah. Now that's a really, really good tip, actually, because the amount of times I've seen products fail EMC only to come back and have more cost associated to the product. So factoring in that right at the beginning of the design makes sense to me. So now that's really, really intuitive thinking, I think.
Exactly. Think about always, you learn in the university, when you generate a frequency is never alone. You have third, fifth, seventh harmonics.
Oh, yeah.
It's like when you throw a stone into the lake, you don't have only one wave, you have some wave in front, you have some wave on the back, and that's what you are taking care in the EMC.
Absolutely. It's been a great conversation today, and I hope we can have you on DesignSpark again real soon. And thanks for giving us such great insight into the world of capacitors.
Thank you so much, Greg.